Welcome to Zebra Aurora Vision Studio. In this tutorial, we'll learn how to separate good parts from the damaged ones using image thresholding and blob classification. To complete this task, we'll need a couple of basic tools. Filmstrip from the image acquisition section to acquire images from the filmstrip control, as well as segment image tool available in computer vision 2D section of the toolbox. We'll start by adding the Read Filmstrip filter to acquire images from a dataset prepared for this tutorial. For detailed information on the filmstrip control, please check our other tutorials. You can find links to them in the video description below. Having the filter in place, we can drag and drop the output image to the preview window and iterate our program once, either by clicking on the iterate icon, pressing F6, or by double-clicking any image in the filmstrip. Next step is adding the ExtractBlobs filter. To do that, we need to stop our program, navigate to Computer Vision 2D section of the toolbox, and choose the Segment Image tool. The ExtractBlobs filter has a couple of different variants to choose from. The one we need is ExtractBlobs Intensity. This filter allows us to extract blobs, which are clusters of pixels with similar properties from the image. In our case, they will be distinguished from the background based on pixel intensity. Using blobs instead of pixels allows us to perform different operations like sorting or classifying them, which is exactly what we need in our program. Let's add the filter inside the process section of our program by double-clicking it. We need to provide it with an input image now. We can do it by connecting the Read Filmstrip output with the input of the ExtractBlobs. Let's execute our program now, then drag and drop the OutBlobs output into the preview window to check the results. As we can see, the extracted blobs are displayed in different colors. We can change the parameters in the properties window to specify how blobs will be detected. By default, the filter is looking for dark objects on bright background, which actually suits our needs. We can easily tweak it to look for bright elements. As we can see, the filter returns white background and holes as blobs now. But let's get back to the previous settings. Using other parameters, it is also possible to change the detection threshold as well as perform additional operations on the detected blobs, like opening, closing, or autofilling holes. There are also splitting parameters, which we'll use in just a second. For detailed description of all the parameters, please check the filters documentation. At the moment, a single preview window displays data from two sources, image and blobs. As we want to focus on blobs, let's toggle the visibility of the image. Now only blobs are visible. We can notice that the blobs of the damaged samples have smaller area. We'll use this to distinguish them from the good parts. To obtain the area of the detected blobs, we need to activate an additional output of the ExtractBlobs filter. This output is hidden by default to keep the program structure clean and easy to read. To activate it, simply right-click the filter and select Property Outputs. These extra outputs can provide us with a lot of interesting information and results. Let's choose Area from the drop-down menu. This will add a new output to the filter, which returns the data we need. To display the data from Blob's area output, let's add a new preview window. We can do it by choosing a different preview layout from the toolbar. Now, let's drag and drop this output to the new preview window. As expected, it displays an array with the Blob's area. This value is expressed in pixels. We can, of course, adjust the preview window size a bit to suit our needs. To be able to compare blobs based on their area, we need to toggle the index preview by clicking its icon. When turned on, it displays the index number of the array elements in the preview window. This way, we'll be able to check what is the approximate area of good and bad samples. Let's see what results we've got for bad samples, which in our case are indexed as 3, 8, and 12. We notice that the largest area of a bad sample is a little more than 1900 pixels, while, on average, a good part has an area greater than 2100. We can safely assume that 2000 is the threshold to separate the good samples from bad. To remove the damaged samples, we will use splitting params located in filter properties. These parameters let us define the conditions for splitting blobs into separate units. Let's restrict the minimum area of our blobs to 2000 by setting the min area. As we can see, all the damaged parts have been removed from the blobs array, leaving only the good ones. If we wanted to keep only the bad parts, for example to count them, we'll just use the max area parameter instead. This concludes our tutorial. If you want to learn more, please take a look at our technical documentation available at Zebra Aurora Vision Developer Portal. You can find links to the sections of the documentation relevant to this tutorial in the video description below. Thank you for watching. For more information on Zebra Aurora Vision software products, visit us at aurora-vision.zebra.com.